So, we are going to see this music box now. I shall play this music box. So, this music box is basically played by rotating a drum, and so this lever allows you to rotate this drum, and as you notice, as I rotate this lever, the lever basically through a small gearing arrangement here rotates this drum. The drum has minute projections on its surface. These projections, when they come in contact with the cantilever, it basically pulls the cantilever up and then releases it as it moves past each cantilever. So, depending upon what song and what pitch of the sound that you want to excite, these projections on the surface of the cylinder are arranged in a specific fashion, so that constant rotation of this drum will excite an appropriate cantilever and a set of cantilevers in succession, and then an appropriate sound sequence is played out. So, you can notice that as I rotate the drum, the projections on the cylinder surface, they pull they pull the cantilever. So, you can see now one by one all these cantilevers are being pulled up. So, if you recollect, this is nothing but initial excitation. You plug the guitar string, maybe pulling it up from the center of the span or from the center of the string, you pluck it. So, you pull it up and then release it. Now, this cantilever is also done like that. You pull the cantilever at its tip. The only thing is, instead of pulling it using your own thumb or a finger, this is being pulled by the projection on the drum. Now, that small thin cantilever is being pulled from here, and then suddenly it is released as the projection passes over. Now, you may notice that this entire plate has a series of cantilevers. These are small thin cantilevers arranged one after the other, and the cantilevers, as you notice here, they are arranged with their lengths being different from each other. So, depending upon which cantilever you plug, the frequency will be different. Okay. So, the shorter cantilever will have higher natural frequency, and the longer cantilever will have a lower natural frequency. So, the pitch of the sound is going to be dependent on the length of the cantilever, and accordingly these engravings on the surface of the cylinder are essentially arranged in a way to excite a particular pitch of the sound. Now, to verify the natural frequency that we will later on find from the cross sectional dimensions of these cantilevers, we would like to record and measure the sound being generated as we plug individual cantilevers. Now, for that reason I have a microphone located here. That microphone is spaced little away from the music box, so that the sound generated from the music box is captured. The sound waves are captured using the microphone. The microphone is connected to a data acquisition board. That data acquisition board is connected to a laptop, and on the laptop I have a software to record that data. Okay. So, let us look at how the data gets captured here when I plug a particular cantilever. So, I am going to plug one of these cantilevers and then start the data recording of this data. Now, you can notice that of course, this the microphone is very sensitive. So, it will record all the sound that it is all the sound that is generated in this room, but definitely I can see that there is this part of the signal which is definitely related to the sound generated from the cantilever. So, this particular data corresponds to harmonic single frequency sound which is radiated or generated, and the corresponding frequency is what you see, because this signal is converted into its frequency domain data. And if I zoom this area of the frequency domain signal, I can see a single tone generated, and that frequency is roughly of the order of 1580 or so. So, 1580 hertz is the frequency which is generated when this particular cantilever was excited. Okay. Now, let me try and get the tone which is from the longer cantilever, and let us see if the frequency is slightly lower. We expect a longer cantilever to generate a lower frequency, and so let me try that out. But you can see from this particular plot that the signal is a pure tone signal, and the corresponding frequency is a pure tone data. So, you can see that after I pluck the the longer of the cantilevers, the frequency has dropped. So, you can see that there are successive two tones which were plucked, and one of the tone corresponding to the longer cantilever is about close to 1400 hertz. So, 1400 hertz, and then let me try and repeat that to get another set of data with a longer cantilever. So, I will record with the smallest of the cantilever, and let us see whether we get a higher than the frequency that we obtained. Yeah, you can now see that I have plugged the shortest of this of the cantilever, and I expected larger frequency, and that is precisely what I am observing here, that the frequency now appears to be more than 2000 hertz. ये इसको क्या हो जाता है, मेरे को समझ में नहीं आता है। तो उसके लिए हटाने के So, I will now excite the one of the shorter ones, and now you can see that instead of the frequency being less than 2000, the shorter beam, when it was plugged, the frequency turns out to be 2090, and that's quite high as compared to the one which we observed 1800 something, which correspond to a longer beam, and that is how the beam length decides what tone is generated. We showed 15 Yeah. Okay. Now, what we are going to do is to give you the exact shape of these cantilever. Now, it looks you may feel that these cantilevers are just rectangular, these cantilevers are rectangular beams, but of different lengths, but actually it is not. If you open this particular plate which has all these reeds of cantilevers, you will find that on the underside, on the top surface it looks very flat and plain, but the underside is cut and the cross sectional dimension at each length at each lengthwise position is not going to be identical throughout. So, what I mean is the cantilever that you observe here is not of constant cross section throughout its length. The cross sectional dimensions do change a lot along the length of each of these cantilever beams, and the shape of one of such cantilever is shown here. So, what we did was we removed this plate, and one of the cantilever was actually measured for its profile. Now, what you observe here is this is the end which is fixed, and the cross section or thickness of the cantilever continuously change along the length of the beam. Now, this brings an important aspect here, that the beam being not a constant cross section throughout, you cannot possibly lump this mass of the cantilever at its tip. If you lump it, then this mass, how do we apportion this mass at the tip of it, and the mass of the beam being larger here, it will influence the natural frequency very much. So, one of the way of modeling this cantilever is to segmentalize it or discretize it using many number of segments, and each segment will be treated like a unit whose transfer matrix can be formulated based on the cross sectional dimensions. The mass properties will be distributed in different segments, that one can take care, but each segment will have its own transfer matrix, and we have seen how Mikkelstadt-Prall method can be used for finding the lateral vibration natural frequency of a beam. Now, in this case we are going to follow the same process. We are going to discretize this entire cantilever into several segments, each segment having its own properties. The material properties are of course going to be the same throughout. The only change will be the cross sectional dimensions. Using the data that we will provide you, you will use that data to find the first mode natural frequency of this cantilever, and the microphone data that we have been acquiring and finding out the frequency associated with that pure tone data. We will compare that measured frequency with the frequency that you obtain using the transfer matrix method. Now, because the cantilevers are being pulled at its tip, it is highly likely that the fundamental mode will get excited readily, and therefore, the comparison will happen between the first mode of vibration, natural mode of vibration of the cantilever with the measured microphone data. The pure tone acoustic signal that it radiates will be corresponding to the vibration that the beam undergoes. Okay. So, this experiment is going to be comparing the measured sound data with respect to the natural frequency that you will estimate for this cantilever. Now, this cantilever is just one of the cantilevers. There are several cantilevers of different lengths, and obviously, each cantilever will have its different shape. So, this is one example where lumping of discrete masses at only fewer degrees of freedom will not definitely give you a right or a reasonably accurate estimate of the natural frequency of the cantilever, and we cannot use continuous system approach, because this particular cantilever has a continuously varying cross sectional dimensions, and it is going to be very tough to solve this using continuum approach or a continuous system approach. So, one of the common way of finding the natural frequency in this case is using numerical methods, and transfer matrix method is one which we can easily use. You can of course use finite element model of this cantilever and find the natural frequency using finite element approach as well, but here we are going to give you the data for each segment, and you can either use finite element model or you can use a transfer matrix method to find the natural frequency.